Welcome back to Daily LeetCode. Welcome to the hyperbolic suffering chamber. If you are a fan of Dragon Ball Z, you will know that this is a chamber that increases suffering for reward. But our chamber is dysfunctional, so it actually just increases suffering. So we need to work on this chamber so that it will actually produce some reward. That being the case, another day, another dollop of suffering, but another chance to prove ourselves to the LeetCode developer team. So I'm gonna jump into it with some comments. We have a comment from Website Lover. Dope name. I also love websites. Day 146. Feels strong, man. Feels strong, man. And I have Arnav Kumar. When will you become famous? Will you remember me? Will you remember me, brother? Feel strong, man. Taru, I did this for about 2 months until I got the job offer. Keep up. Hey, feel strong. Yeah, this is true. I wouldn't say we're really looking for work right now, but yeah, it would be cool. I'd just like to finish all the problems. Forget that. We've been talking in the Discord. I'm coming for the international grandmasters in competitive programming. Okay, we're coming for them. They're shaking in their boots right now. Okay, because the hyperbolic coding chamber is coming. It may not be this year. It may not be 2022, but in 2032, 2032 they gotta watch out because we're coming. But we have another comment from Cheb Master. Nice job, man. Keep it up. You keep it up, dude. You keep it up. And we have Island Eagle with nice hat, brother. You know it. You know this. And then we also have a comment from Jorge Mejia. Doing this too on day 90 something. Keep going. It'll all be worth it in the end. True, man. There's nothing like proving ourselves in the crucible. The crucible or the Colosseum. I know nothing about history, but I imagine the Greeks or the Romans or whoever was in the Colosseums or the Crucible, I imagine they were rewarded with great riches upon exiting the Colosseum or the Crucible. So that is the goal. That is the goal. But yeah, it's just interesting. I know the last few days I said I was ready to run. I think I'm ready to fry, but the schedule is like the last. I feel like it's just a missing piece. When I was doing LeetCode in the morning, it was fire. It was fire. I was able to use the freshest time of the day to pretty much do all the stuff I needed to do. That way, the roller coaster of emotion and other things that happen throughout the day, they wane on the human brain. So you're just less ready. Got less brain sauce, to lather on those LeetCode characters. But yeah, it's just an issue because I can't, for some reason, get myself to get out of bed in the morning. So I need to do, I pretty much wake up 30 minutes before work and then jump into it. So I think I just need to wake up earlier. Today was better. I woke up about an hour and a half before work and just did some supplemental reading and stuff like that, which was good. But that would be ideal. I think if I could get up like 3 or 4 hours before work, that would be perfect. It would just be able to get it all over with at the right pace, no rush, and then I'd be ready. But that's just a secret sauce. If we could get that, I think if we could get that going, we would be a well-oiled machine. That way, yeah, usually the reason I cut it down from 30 minutes to 1 hour and 35 or whatever is usually because of how much brain sauce I have left at the end of the day. So if we could do it in the morning, that would be better. One of the issues that comes with that, though, is that I feel like the brain is sort of like a car. I mean, before you go out into the winter, right, when it gets cold, you have to turn your car on. You have to let it sit, marinate in the chicken broth, right? And then the engine is ready to go. And I found that to be relatively true for LeetCode. I feel like or just brain-intensive tasks, I find that it's much easier to focus after the day is through. Not through, but like in the midday. Like 12 p.m. is ideal focus time. I'm like a laser. But 7, 8 like it is now, not as good. The morning time I have more brain sauce, but my mind is more scattered. It hasn't been lasered in yet. Probably because I'm just waking up, and on my boot cycle, my brain has to clear the RAM of all the nonsense of the dreams that we just did. So yeah, that is just not flame. So if we could wake up earlier, that would pretty much, the biggest change we could make right now to the grind would be to wake up earlier, and it would be the biggest ROI. So I need to find a way to make that make sense. We might have to buy the wrist bracelet, or maybe there's an app. You know what? We're going to institute a new policy in the hyperbolic coding chamber. Maybe there's an app we can all download, and we're all going to set a timer to wake up at the same time. And if one person doesn't wake up, then the alarm just doesn't stop. And so I'm thinking that might be the wave. If you guys know any vendors that could make that possible, that might be the solution. But yeah, I need to figure that out. So yeah, it was kind of what I was saying before in a previous comment. I woke up earlier for like 2 weeks straight, but it was because of the novelty of starting something new. It was easier to wake up earlier in the morning. And I remember I was responding to a comment that someone wrote about how to stay motivated or something like that. And I was like, the real problem is the plan B that we're experiencing here, where it's like, it's easier to do the thing with the motivation of the novelty of starting the thing, but then once that dissipates, that's where you truly can make progress, really. So it's really hard. I guess what I'm trying to say, I feel like the secret in staying motivated is in actually, it can only be found in literally being unmotivated. I don't know how to explain it, but it's just the way it makes sense to me. I think that's the cheat code, because when I'm already motivated, I don't need any motivation to get what I need to get done. So, and then there's a whole conversation about motivation versus discipline, but we're too deep in the sauce. I guess what I'm trying to say is I need to find a way to wake up early. And the only way to actually know if I've solved the problem, kind of like with running a computer science test case, is for the environment for which I'm running the test case in to be consistent. And it's just not consistent when I'm overly motivated. So right now is the best chance I have of solving the actual solution and the solution actually sticking, because it's not working. So we're going to do a random walk and see what we come up with. That being said, what we're not going to be doing randomly is LeetCode problems, because we do have a problem we're working on called ones and zeros. So that's what we're going to continue to work on today. I was looking more into Dijkstra's. I still think it's possible. I'm not exactly 100% convinced that Dijkstra's will be the most beautiful solution to this problem. However, it will get us where we need to go, potentially. And I think this problem will serve as, if anything, introduction to dynamic programming. I foresee that we'll probably be stuck on this problem for a week. And that's mostly because I don't think I've ever done a dynamic programming problem in a way that is actually DP. For example, one of the very popular dynamic programming problems is trapping rainwater, and my solution is the most undynamic programming problem solution ever. It's more of just like a optimization across the space of the problem rather than dynamic programming. But the ideal solution to that problem is DP. So any time there's DP, I always find a way to slither past it. It remains to be seen if this is possible for this ones and zeros problem, which I think is why I'm having so much difficulty. So if I had to rate the problems I am absolutely the worst at, and I'm sure I share this with a lot of other people, it is DP, dynamic programming. I haven't done many of them, and also I always find a way to not do DP. So that being said, we just need to find a way to wake up earlier. So today I say we're going to do a solid 40-min sesh. And hopefully it'll be beautiful. It'll be magnificent. It'll be a session we didn't expect to have such beauty hidden beneath its layers. So we shall see. And I'm just going to jump into it. So here we are. We are back once again. We're trying Dijkstra's for this problem, for which it does seem possible, but there are some things that are a little bit worrisome. For one instance, we should make sure that our Dijkstra's algorithm makes sense. We have entry, distance, and parent, the 3 Boolean arrays for which we need to make this make sense. We have v, which is the current vertex to process, distance, which is the best current distance from start, as well as the code to init the bool arrays. And that comment actually doesn't add much, right? From here, right, we need a new comment, right? We'll say something like distance sub v, right, which is our start index, which is our start vertex, right? The distance array stores the distances of a vertex from the start vertex, right? And usually the start distance from something to itself would be 0, right? Usually. So that's what we say here. Usually distance of start, distance of start usually distance of start to itself is 0. And v is start. Well, v is equal to 0, which is why we're pretty much saying the first index in the array is the starting index. From here, we're going to iterate, right, over vertexes, right, while they haven't been processed. So if it's not in the tree, it hasn't been processed yet. And the tree we're talking about is the shortest path spanning tree, which is created when the algorithm is completed, I believe. Here we're going to iterate over our neighboring edges, but it actually makes more sense to say evaluate neighboring edges, right? And that is technically what we're doing, right? We're saying w is equal to 0, right? Where w is our candidate next vertex, and we're iterating over all the possible strings in the array. Additionally, we have the weight of the string, which we're kind of saying is the length of the string. To do is this weight the move? And what we're doing here is what we're really trying to do is update the distance for all vertexes. We want to update the distance for all vertexes we have a better path for. Right? So the v does not equal w here is just a check to make sure that we don't process the vertex we're currently processing, or update the distance for the vertex we're currently processing. But we'll say distance sub w, and distance sub w holds the distance of a vertex from start. If we're saying distance sub w is greater, right, than distance of v plus weight, basically saying that the current distance from start is larger, right, than this new distance that we could create, or this new path that we could create if we use the current vertex we're processing, right? So distance of v plus weight, all right, then we'll say, okay, we'll update the distance from start because we have a shorter path, and we'll update the parent. Now here, we're saying that select next vertex to process that isn't in tree. That's not exactly true, because what we're really trying to do here is choose the next vertex. We want to choose the next vertex. Choose the next unprocessed vertex with the shortest distance to start, or from start. So to do that, we're iterating over all the vertexes, which is really just every element in the array, we don't have to do the W does not equal V thing, because once we enter the loop, right, we already set it to processing the vertex to true. So it's already processed because it's in the tree. So this case here would pretty much excluded. And right, distance. So we're looking for the vertex with the shortest distance from start, right? So what we see is that distance is greater than distance of W, right? Which means we found a shorter distance. We could also say distance of W is less than dist, which is another way to do it. But then we're set the new lowest distance to distance of W, and the next vertex to process the V, and see if we can find the shortest, the next unprocessed vertex with the shortest distance from start. So this Dijkstra's does look fine to me. If we run it, we're getting some strange output, probably because we haven't configured the problem to make sense with this version. Right, so if we look at our output, we'll have 0, 4, 6, and 1. This is the distance array, and the distance, or the weight, or the distance, right, to these vertexes. Pretty much this word, this element here, what's our input? Oh, it's the regular input. I'm just now realizing we're literally missing something. So our distance array and all of these can't be 4 elements long, because our input array, our input graph, is 5 vertices long. So this looks a little more sensical. So our distance array, we know that distance from start is distance from start to 4. The distance from 4 to start, from vertex 1 to vertex 0 is actually going to be 4, with the edge weight just being the length of the string. We see that all the values in the distance pretty much end up becoming the length of the strings. We'll also see that in the parent array, the shortest path spanning tree ends up just being every node starting from the starting vertex, going to the specific vertex. Maybe we'll get a bit more intuition as to why this is. Well, I think a better question to ask is, what output am I expecting? I guess I'm expecting output that leads me closer to the answer, but it doesn't quite make sense, because the shortest path (1, 0) So our current output makes sense because our graph is fully connected. So the shortest path from a vertex to start is just going from start directly to that vertex. I think we'll find some actual value once we actually try and create the longest path. once we actually try and create the longest path, so the weight of the edges can still be the string length, but we want the longest path. Longest path being comprised of many vertices. The longest path, this might not provide a lot of value because the longest path would pretty much always be going through every other vertex in the tree once and then ending up at start. If we did that, that doesn't quite add a lot of value. Maybe that doesn't add a lot of value. Maybe that doesn't add a lot of value. The shortest path is just always, if the longest path is just always taking all the other paths and then taking the last one. I think the fact that the whole graph is fully connected kind of takes away the fully connected. If you did fully connected, Wait a second. We don't want the weight to be the length because length doesn't communicate the complexity of the choices. Communicates the complexity of the choices is how long the path is. So the weight of each edge should just be, the weight of each edge should change. You'd want the length of each edge, or the weight of each edge, to pretty much hold Wait, we want the weight of the edges to represent something else. I think there are two paths here. One, the potential edges change for each vertex. Neighboring edges change. Depending on viable options. Second one is weight for edges should, the weight for the edges should represent number of nodes to get there. And I think that's the DP approach, the second one. So I think this first one means we could still recycle Dijkstra's. But the first one means we could still recycle Dijkstra's. The second one I think would mean throwing this all in the trash and using an array for DP. Well, let's look at this case here of 0, 0, 1. We have m is equal to 3 and n is equal to 9. If you start here, the number of zeros you're allowed to have are 9, and the number of ones you're allowed to have are 3. If that's the case, if you start here, then you can't choose any of the other ones after this. So if you choose 0, 0, 1 and then 0, 1, 1, then you can't choose anything after it because the other ones all have ones, and that would take you past the limit. How can we rate the desirability with this information? If we did m, which is 9, minus 0, we'd get 8, right? And 2 minus 2, which would give you 0. I would give you 8 as the remaining zeros and ones left. If we did it for this one, you would get zeros. Oh yeah, but they're all the same since you're starting here. And then we'll have 3 m's. I mean, no, you can have it. M is 0. You can have at most 9 zeros. So there'd be 6 zeros left and 2 and 1 1 left, which would give us a sum of 7. This would also be 7, presumably. I think this would be a better way of weighing the edges. This way we wouldn't have to change Dijkstra's. We just have to run it multiple times, and the shortest path actually would give us the answer we're looking for, because it should be the path with the most distance. So maybe we can make a function called, we'll just call it calc weight. What would we need? Right, we'd need the current m's. Well, we need the starting m's. We need start m, or initial m and initial n, as well as cur m and cur n. Then from here we could return pretty much what we did down here, which was initial m minus cur m Oh no. And there's one more case. If a value would take us below, so for example, imagine we had something that would have like 5 ones in it, it would take us to negative, right? And so we'd have pretty much a possible edge. If we had like, a bunch of ones here, we could end up with a value that would give us a negative edge. There's 2 issues with that. Dijkstra's I don't think is compatible with negative edge weights, and additionally, we would just always choose a negative edge weight. So we need to calculate the value. And so we'll say initial m minus cur m plus initial n minus cur n. Right? And what we'll return is if value is greater than 0, greater than or equal to 0, then we'll return value. Otherwise, we shall return infinity. Because if it's a negative value, right, it'd be too good of an edge, and we don't want that to be the case. Now, I think one other thing with this that doesn't quite fit yet is that if we were to calculate the weights this way, the weight would kind of be dynamic, which probably isn't good for Dijkstra's. Even if we set it all up, if we did it all up front, you know what? Maybe that works. If we did it all up front, maybe that's ideal. And then we could just follow the parent tree up. And then as soon as we pretty much break it, right? As soon as we break the rule, or m or n is negative, then we'll pretty much have our answer. We still have to call it multiple times though. So weight here. We actually need, we need that function from earlier. Ones, right? We'll pass in a string and it will return a tuple of numbers. If s sub I, 2 lowercase, equals 0, then we'll do ones plus equal 1. Otherwise, we'll do zeros plus equal 1. And then for the weight, what we can do is do calc weight. And then we'll get const zeros and ones for get zeros and ones for strs sub w. And we'll need the calc weight. Initial m will be m. Initial n would be n. Cur m. It's not really cur m and n. It would just be we'll use it anyway. We'll do zeros. So at the end here, what are the actual weights we're looking at? 0. Looks like this one would be 5 minus 3, which would be 2. And 3 minus 1, which would be 2. That looks correct to me. We have 1 and 1, which would be 2. And then we have 7, which does make sense. This is not going how I planned. Each vertex, the weight for edges should represent the number of nodes. What if we combine these options where we don't make the graph fully connected, and the neighboring edges you can actually choose depend on your already chosen options? I think we could combine this. What if no more fully connected graph, edges chain based on node? The edges change node. Next unprocessed vertex is short distance from start. I think changing the graph from fully connected, the edges changing on vertex viability makes more sense. The issue I'm thinking of though is if, for example, we could go from, if we already have one, let's go back to our original example. If we take this one here, our potential edges would still be all three. So they would both still give us an M and N that's positive. But the one that would be cheapest nine minus 3 is 6. That doesn't even feel like 40 minutes. I actually don't even know where the time went. Wait a second. I want to try something. If I copy this link and I try my old, I think we did a greedy solution. I think we had one with a greedy solution. I had 2 for loops. No, wait, this can't work. It doesn't make sense for this to work. If we look at the edge evaluation, we have 9 and 3. We have 1, 0, we have 8, right? Plus, so we have 9 minus 1 plus 3 minus 2. 9 minus 1 gives us 8. And 3 minus 2 gives us 1, giving this, wait, 9. If we look at this one, we'll have 9 minus 3 and 3 minus 1. 9 minus 3, 6, and 3 minus 1 is 2. 6 plus 2 gives you 8. Surely this couldn't work. If we copy this, and I'll reset the code that exists in here, I'll go above it and paste it. So let's just calculate the weight based off the M, and what if we said annotated for tuple strs equal to strs.map string, right, to the string, right, and the new weight, which would pretty much be calculated by calc weight of M and I need to make this a little bigger, it seems. Ones, and we'll have a function, right? Const zeros, ones equals get zeros and ones of the string str. I'm going to return 0 for now, and then just print tuple strs. The output for test case 2 should be 2. What if we then sort the tuples based on their in descending order and then what we'll do is we'll say let count equal 0. We'll return count, and we'll just iterate over the tuple strings, except we'll try a new greedy algorithm where the weight isn't the weight of the string, or the value isn't the value of the string, but it's based on this new function which calculates the weight differently. Let's go I equals 0. Strings dot length I plus plus. I'm pretty much going to say while m does not equal 0 or n does not equal 0, we're going to pretty much go through it in order. I mean, if m does not equal 0. I guess we pretty much want to choose, so we'll probably do something like this where we'll have an pretty much need this to stop eventually. We'll pretty much assume that it's going to run forever. I would say while m does not equal 0, actually, yeah, I think we can do true, and we'll figure out a way to exit. We'll have a set for which would be a new set of type number for indices. This is going to be within a for loop, and we'll just iterate over literally all the strings I plus plus, and we'll just choose the one with the smallest weight all the time. To do that, we'll have to say that weight is equal to infinity. Actually, no, we want to maximize this weight value. So we'll say weight is equal to negative infinity. And if m does not equal 0, right, which m does not equal 0, n does not equal 0, which means there's still something to find. And let's just say the weight for the string oh yeah, well, we have tuple strings, right? So we're actually iterating over tuple strings, right? And tuple strs sub I sub 1, which would be the weight, right? If our weight, since we're looking for the largest weight, if weight is less than 2 plus sub I sub 1, then we'll say that weight equals equals 2 plus sub I sub 1 I should just said it's an array of just that weight is equal to 2 plus sub I sub 1. Now you have the smallest weight. Now you want to choose this index, and if it hasn't been chosen, we'll say that I is less than stirs up length. Say v is equal to -1. If we iterate through the loop and there's pretty much no vertice, v equals -1, then we'll just do break. But we'll say v is going to be equal to I. Else we'll say chosen.add v also count plus equal 1. Also, you need to get the zeros and ones for stirs sub v. This is mostly so we can do m minus equals zeros and minus equal ones. If m is greater than or equal to 0 and n is greater than or equal to 0. Oh, this is very ghetto. M minus zeros. Maybe our best, we'll just print our best option was something's wrong here. Best option was 1. Which makes sense. But then it says the next best option was this value, which makes no sense at all. Oh, stirs sub I. I see. We need to be using tuple stirs I sub 0. Oh, I'm literally printing the wrong thing. Want zeros and ones, we're going to do sub 0 here. And then I'll try this one last thing. I'll start, which would be an index, and it's going to return a number. I'm going to say chosen.add start. Which is going to be the start index later on. Oh, this is so the code has become spaghetti. I need to come back tomorrow with a fresh brain and try this one. M minus zeros is greater than or equal to 0, and n minus 1s is greater than or equal to 0. M minus equal zeros, n minus equal 1s, ct plus equal 1, chosen dot add start. Then we can copy all the code from here into here. Yeah, that's fine. And then we should just get the same answer if I do work, stirs, m, n, and 0 as the start index. And then we should paste the work function in here. Oh my god, this is so bad. I think I lost the intuition on what I was trying to do here, but basically I think with a different function, we could make this make sense. The greedy option might still work, but we'll be back tomorrow to try with a better version.